Hi all, today we discuss section 3.2, the algebra of linear transformations. In this section we have theorem 4. Let V and W be two vector spaces over the field F. Let T and U be linear transformations from V into W. The function T plus U. So this is the sum of two linear transformations that is defined by T plus U of alpha is equal to T alpha plus U alpha. This is for all alpha belongs to uh, V is a linear transformation from V into W. If C is any scalar, here we have scalar C. This is C is any element of F, that is any scalar. The function Ct. Okay, this is again a new function Ct defined by Ct of alpha C times T alpha. This is what we call the scalar multiple of a transformation. Is also a linear transformation from V into W, and the set of all linear transformation linear transformation from V into W together with these two operations, the above said operations, is a vector space over the field F. So first we need to prove that consider set of all linear transformation from T from V into W, where this T is a linear transformation from V into W. We need to prove that this is a vector space with respect to these two operations. Yeah, so that is the idea. So first we will prove this vector space by proving the 10 axioms. First we prove the closure property of this. We will prove that T plus U belongs to again this set. I call for the time being I call this set as S. In the textbook we have a conventional name for this set. We will later will give the concerned name for this set. For the time being we consider this as S. So we prove that this belongs to S. To prove this, we need to prove that this T plus U is a linear transformation. Okay. So how will you prove this is a linear transformation? T plus U of C alpha plus beta. By definition, this is equal to obviously this is T plus U is a function from V to W because of this definition. So this is defined as T of C alpha plus beta plus U of C alpha plus beta, but T is a linear transformation because T comes from this set, so that can be written as C times T alpha plus T beta. This is the definition of linear transformation, and plus we have C times this U alpha plus U beta. So this is the definition of linear transformation as this U is a linear transformation. Now combine these two, the first two terms, so that will give C T alpha plus C U alpha, that is C times T alpha plus U alpha. Both are elements of W. T alpha and U alpha elements of W, and W is a vector space of the same field F. Then this plus you can combine the other two, T beta plus U beta. So this is beta here, this is beta. Now what is T alpha plus U alpha? That is by definition that is T plus U alpha. Similarly this is T beta plus U beta, that is T plus U of beta. So now this takes the form, this is equal to C times, we can write as this is T plus U of alpha plus T plus U of beta. This shows that T plus U is a linear transformation as it satisfies the condition for linear transformation. So once the axiom 1 is proved, so closure property is there. Now we need to prove that the associativity of T, U and W from this S. So we take T, W, T, U, W. Suppose I'll write this T1, T2 and T3 or from this S to prove this these three linear transformation arbitrary three linear transformation satisfies the associativity. So we need to prove that T1 plus T2 plus T3 the same as T1 plus T2 plus T3. How will you prove? These are functions. Anyway, we have proved the closure property of summation addition of two linear transformations. So we can say that all these are elements of S. Then all these are linear transformation from V to W. So to prove this, these two functions are or linear transformations are same. We need to evaluate all two linear transformations at all the points alpha of V. So once you to prove this, we consider T1 plus T2 plus T3 of alpha, T3 of alpha. So by definition, this is same as T1 plus T2 of alpha plus T3 of alpha. So again, by definition, you can write this as T1 alpha plus T2 alpha plus T3 alpha. Okay. Now you can verify the other part, T1 plus T2 plus T3 of alpha. Now use the same definition, you can say that this is first T1 alpha plus T2 plus T3 of alpha. That is again T1 alpha plus T2 alpha plus T3 alpha. So this shows that the associativity is there. You can associate this T1, T2, T3 in any manner. So this shows the associativity. Now we need to prove that the existence of identity. So for that we prove the zero transformation. 0 of alpha is equal to 0 for all alpha belongs to V. Then you can evaluate T1 plus 0 of alpha or T plus 0 of alpha. What is T plus 0 of alpha? That is T of alpha plus 0 of alpha. But 0 of alpha is always equal to 0. Then this is T alpha plus 0, that is equal to T alpha itself. So this is true for all alpha belongs to V. And similarly, you can prove that 0 plus T of alpha, that same as 0 plus T alpha, that is again T alpha for alpha belongs to V. So this shows that T plus 0 of alpha equal to T alpha, that is equal to 0 plus T of alpha. So that is a T plus 0 equal to T, that is equal to 0 plus T. So this shows the existence of identity as the zero transformation. Now we have the inverse. If you can inverse with respect to this addition. So once you consider a T from this S, then define minus T, okay, minus T of alpha as minus T alpha. Now you can easily prove that T plus minus T of alpha equal to T alpha minus T alpha, that is equal to 0. Similarly, you can prove minus T plus T. So this shows that T minus T equal to 0 equal to minus T plus T. So you can show that once T belongs to S, then this minus T, when you define minus T in this manner, you can say that minus T plus T equals 0. Now it remains to prove that the minus T is also an element of this S. Okay, that we will prove in the next session of axioms of scalar multiplication. So we have one more thing here. If we consider T1 plus T2 of alpha, that is same as T1 alpha plus T2 alpha, that is equal to T2 plus T2 alpha plus T1 alpha, because T1 alpha and T2 alpha are elements of W and W is a vector space. So vectors of W commute, so you can write it as T alpha plus T2 alpha plus T1 alpha, that is T2 plus T1 alpha. This shows that T1 plus T2 is equal to T2 plus T1. So this forms, once you prove the closure property of the scalar multiplication, you can prove that these axioms show that this set S along with this vector addition is an abelian group. So this completes the 5 axioms. Now we have 5 more axioms to prove. So the axioms corresponding to the scalar multiplication. Now we will prove the axioms corresponding to the scalar multiplication. So the scalar multiplication is defined as Ct of alpha is equal to C times T alpha. Now we'll prove this closure property of this, that is Ct of this. Ct is an element of, again, element of S, so we need to prove the closure property of this, or Ct is a linear transformation. So by taking this as Ct of, I'll take it as some d alpha plus beta. We need to prove that this can be written as d times Ct of alpha plus Ct of beta. So by definition, this is Ct of this is same as C times T of d alpha plus beta, and T is a linear transformation, so this can be written as C times T d T alpha plus T beta. Now you multiply with C, you can write it as C d T alpha plus C times T beta. So that is equal to, you can write this as D times, so we'll write this as C D times C times T alpha. C times T alpha is Ct of alpha, plus this is C times T beta, that is Ct of beta. So this shows that Ct of d alpha plus beta is equal to d times Ct of alpha plus Ct of beta. So this shows that Ct is a linear transformation. Again, that is an element of S. So this proves the closure property of the scalar multiplication. Now you can prove the associativity of scalar multiplication. That is C1 C2 T times T is equal to C1 C2 times T. Okay, so this is because we need to prove this one. So we start with the left side, C1 C2 T alpha, that is equal to, by definition, this is C1 C2, this is C1 C2 of T of alpha, that is equal to C1 T2 C1 C2 T alpha. So this is same as when you consider the other association. I'll write it as, that is C1 times C2T of alpha. So this is same as C1 times C2T of alpha. Okay. This is same as C1 C2 of T alpha. So these two are same. So you can say that the associative property is already there. Now we have the associative property of distributive property. So we have this is C1 plus C2 of T, that is same as C1T plus C2T. So this is because we'll prove this by evaluating both sides. So when you evaluate this of alpha, then you can get that C1 plus C2 into T alpha, that is C1 T alpha plus C2 T alpha. Okay, so this is the LHS. Then what is RHS? RHS is this of alpha, that is C1 T of alpha, that is C1 T alpha, C2 T of alpha, that is again C2 T alpha. Then both are same, so we can say that this distributive property is there. Now we have fourth one, 1 times, we define I alpha is equal to alpha, and this I can act as 1. Sorry, this is not I alpha. I'll write it as 1 alpha. This 1 comes from the field, and T comes from the set S. Then we need to evaluate this of alpha is same as T alpha. So this is because when you write this is a 1 times T alpha, that is equal to T alpha. Okay. Now this T alpha, this can be written as 1 times T is equal to T for all T belongs to S. So this shows that 1 into T is equal to T. Now finally we have 5, that is same as C times T1 plus T2 is same as CT1 plus CT2. Okay, this can be proved by evaluating each function, each side LHS and RHS at alpha. Then this of alpha will give C times T1 plus T2 of alpha, that is C T1 plus T2 of alpha. This is this of alpha, that is C times T1 of alpha plus C times T2 of alpha. Then you can write this is equal to C times T1 alpha plus T2 alpha, that is C times T1 alpha, C times T2 alpha. Similarly, this will be C times T1 alpha plus C times T2 alpha. So this shows that S, we have already defined that as the set of all, I'll write that S is equal to set of all linear transformation from V to W. Okay, such that is linear transformation. This is a vector space over the same field F, and we denote this vector space as LVW. LVW stands for set of all linear transformation from V to W, and V and W are two vector spaces defined over the same field F.